example design of doubly reinforced concrete beams. Okay. All right. So this is just for the cross-section design. So what in this case we're given a couple things. We're given that the maximum depth of the tension steel D that we want, D max, is 25 inches. We did a structural analysis, found the required moment strength. That's a weird number. Let's just go with 780 kip feet. Yeah? Is that okay? All right. And then we're told we have to have a minimum depth. D min for the compression steel is 2.5 inches. Yeah, D min prime. Yep, for the compression steel. And then I would like to design a rectangular beam cross section of 4 KSI. So FC prime is 4 KSI with grade 60 steel, so the yield strength is 60 KSI. Okay, and we would like to find, okay, so it says find, well, when we say design, really what we really need is AS required, and if we need it, AS prime required. Okay, the area of tension steel and area of compression steel that's required for both. And we're also told, well, let's see, what a reasonable ratio, like if I look here, it's like it's a 2-to-1 ratio, right, for B to D or BH, right? So a reasonable height here would be like, you know, D is the height is approximately D plus approximately 2.5 to 3 inches, depending on, you know, the bar size that we choose. If we're going to use 25 inches, so maybe using 28 inches would be good. And then if we're looking at a 2-to-1 ratio, then maybe we'll use a B. We'll use a B of 14 inches. Okay. All right. Okay. So, all right. So great. So this we have a big clue about the cross section. So here, if I consider the schematic that I'm looking at here, okay, I have, I'm going to end up drawing, I'll pause. So our final design is going to be some, well, I'll tell you right now, the singly reinforced part is not going to be enough, okay? Obviously, otherwise it's not going to be a thing, right? And then here, this is going to be, so our final design is going to be trying to determine AS prime and AS. Based on what's given, the given information, I'm going to say that D prime, we're going to start with a D prime of 2.5 inches. We'll have a D of 25 inches. And then a B of 14 inches. Okay. If you want to go smaller, then you'd have to design starting with smaller numbers, right? Okay, and then this additional distance right here is 3 inches. Okay, that's 3 inches right there. So we have, so first we're going to attack the singly reinforced part. Okay, and let's see here. So here I would have the singly reinforced part, and in the singly reinforced part, let's see, singly reinforced. So here I'll call this, I'll put this right here. This will be AS1, and we'll say singly reinforced design. So basically what we want is MN1, okay? We're trying to get MN1 here, okay? So I'm going to guess a reinforcement ratio. Where's my textbook? So I'm going to guess a reinforcement ratio. There's a temptation sometimes to guess a rho associated with 0.005. Okay? But the reason that is problematic is because a couple reasons. One, you know, that rho of 0.005 is associated with a area of steel AS1, right? And the main reason that's problematic is that when we select the actual bars from AS required, we're going to be rounding up, right? And we're going to add more steel than the target reinforcement ratio, and that might take us into that transition zone for phi, and so that would be problematic. So really, like if I look over here and remember this table in your textbook, so grade 60, I have a rho of 0.005 of 0.0181 for FC prime of 4 KSI and grade 60 steel. I'm going to just choose rho of 0.0075. Okay, so my rho target for my singly reinforced part, I'm going to use rho of 0.0075, and for 4 KSI concrete and grade 60 steel, that is 0.0138. 0.0138. Okay, so by that choice right now, I have specified a strain profile, right? And that strain profile is essentially the same for all 3 drawings. Yeah? Okay. And let me draw a vertical line. So my strain profile I've established like that. Okay. And this is 0.003 strain, compression, and etc. Epsilon s. Okay. Yeah, that's pretty good. Okay, and now I can now that I have this, I can calculate an area of steel associated with this. So with this one, I would have, let's see, based on this, AS1 is rho 0.0075 times B times D. Yeah, and that would be 0.0138 times a width of 14 inches times 25 inches, and what'd you get? 4.83. So 4.83 inches squared. Okay. And so, oh great, so I know that, and now I want to calculate MN1, right? And so shoot, I could, to visualize this, I can draw my stress profile, which this is exactly as we had talked about right here. There's some neutral axis depth, CNA, and this, there's some equivalent stress block, A, and this is 0.85 FC prime. I have a resultant CC here, and then a Fy because it's yielded, and TS1. Yeah, okay. And so do I know CNA? Do I know the depth to the neutral axis, CNA?
By similar triangles.
Yeah, by similar triangles, because I know epsilon s based on my reinforcement ratio is I know this point right here is 0.0075, right? So from similar triangles, I know that CNA, I can, let's see, my calculation for CNA.
CNA over 0.003, right?
Yep. So it would be, I would have, let's see, CNA over 0.003 is equal to this distance, which is D minus CNA, D minus CNA over 0.0075, right? And I know D is 25 inches, so if I go ahead and I solve this out, let's see, I will get okay, I want to just do the shortcut, but here I'll do the algebra real fast. Okay, it's let's see, 0.0075 CNA equals 0.003 D minus 0.003 CNA. Yeah, and D is 25 inches, and so CNA is whatever, what's that, 0.003 times 25, is that like 0.075? Yeah, 0.075 inches divided by 0.0105, I believe. And what is that?
7.14.
It's 7.14 inches. Okay, CNA 7.14 inches. And now that I know CNA, I can determine the depth of the equivalent stress block. Okay, and so A is beta 1 times CNA, which is 0.85 times 7.14 inches, and that is 6.07 inches. And from moment equilibrium, and I won't write that equation out, but here from moment equilibrium, I'll write the equation out. I won't show the drawing, but here Mn1 would be Ts1 times d minus y bar. Yeah, I have a rectangular stress block, so this would be As1, which is 4.83 inches squared, times Fy 60 ksi times d 25 inches minus 6.07 divided by 2 inches. And that is, Mn1 is 6,365.46 kip inches, and divided by 12, 530.45 kip feet. And what's my strength reduction factor? 0.9, because we chose rho of 0.0075, or the strength. So phi Mn1 is 0.9 times 530.45, which is 477.41. And this is definitely less than the 7, did we say 80? Kip feet. Okay? All right. So, okay. So I could, there are other things I could do, but I doubt it's going to make that much of a difference. Is that I could say, well, shoot, you know what? Let me up the amount of steel, because remember rho of 0.005? Rho of 0.005 is 0.0181, right? Will that get me to, I could do that. I could say I'm going to put exactly 0.005. You know, I'm going to get the strain to be exactly 0.005, and I could maybe get closer to 780. I don't think so. It will be close. It might get closer, but I don't know. I don't think I could get, I don't know. I didn't never checked. Okay. Okay. But that would defeat the point if our singular reinforced beam satisfied this. Okay. So now I'm saying, okay, well, shoot, I don't have enough. I can't adjust D. I can't adjust B, right? I'm stuck with those. I need more steel. I need more. I need compression steel to balance it out, to keep the strain profile from not getting all crazy or not changing. Because the fact of the matter is, with that, if I just add tension steel to this, then I'm changing my strain profile, right? And it's getting more brittle. You know, it's getting closer to 0.005, right? If I just add steel. If I just add tension steel. So I have to add both tension steel and compression steel to keep that balance, keep that equilibrium, right? And this right here, we need AS2, and we need some sort of AS prime, right? And the strain profile is the same, so there's no mystery there. That strain profile is the same. Okay. Like this, that strain profile is the same, and then I have a force or stress and force profile. I cannot use the concrete in compression because that's already been used. I only have the compression stress in the compression steel, and then I have CS prime, and then I have the equivalent Fy for the tension steel, and and I call that TS, like that. Okay? Oh, TS2 right here. And I have to maintain equilibrium. So that's no big deal. I have to maintain TS2 equals CS prime. And from moment equilibrium, Mn2 is TS2 times D minus D prime. You agree if I took moments about TS2, it would also be CS prime times D minus D prime. Okay, and here, this is d prime. This distance right here is d minus d prime. Okay, and this is 0.003. Our CNA here is still the same. It's still that, I think, 7 point something, 7.14 inches, right? So what's going to be important here, okay, is a couple things. How much more moment capacity do I need? What is this Mn2 that I need? Okay, and then did my compression steel yield or not? Okay, all right. So first, okay, so 1, 2, I'll call it 3. 3 additional moment capacity needed, and that'll be Mn2. What is Mn2? Well, Mn2 is from the BDR, phi times Mn1 plus Mn2 is greater than or equal to Mu, and so Mn2 is equal to, or greater, we want it to be greater than or equal to Mu over phi minus Mn1. And this is, Mu is 780 divided by 0.9 minus Mn1, which is 530.45. And can you calculate that for me?
Oh, sorry.
Oh, no, it's all good.
Minus 530.45.
Yep.
247.33.
247.33 kip feet. So that's the additional moment that I need. Okay, and that means if I go and I look at moment equilibrium, the additional TS2 that I need, I can right here. So, well, shoot, 1, 2, 3, 4 additional tension steel AS2 from moment equilibrium. That would tell me, well, let's see, Mn2 is equal to TS2 times d minus d prime. The strain profile hasn't changed, so this is the same as 247.33 kip feet is equal to AS2 Fy times d minus d prime. And the only thing we don't know here is AS2, because Fy is 60 ksi, d is 25 inches, and d prime we said is 2.5 inches. So AS2 from here is equal to 247.33 kip feet. Don't forget the unit conversion. 12 inches per foot divided by 60 ksi divided by 25 minus 2.5, which is 22.5 inches, and you got 2.198, so 2.20 inches squared. So that's the additional tension steel that I need. So we already have an answer. We have, essentially, this tells us that AS is equal to AS1 plus AS2, and so here this would be, we said AS1 is 4.83, so 4.83 plus 2.20, and that's 7.03 inches squared. So AS, the area of steel required on the tension side, is 7.03 inches squared. Okay?
That's just on the tension side.
That's just on the tension side. Now we have to determine the compression steel. So 5 compression steel needed, and that's going to be from our equilibrium equation, AS prime, and we're going to use equilibrium for this, which is that TS2 equals CS prime, and here this is AS2 Fy equals AS prime Fs prime. Okay, so the question is, what do I use for Fs prime? So did it yield, did it not? So I have to check, what is my strain strain in compression steel. So I'm going to use similar triangles to determine epsilon s prime. And here, by looking at my drawing right here, here is my compression steel. This is epsilon s prime, and we know this distance is d prime. And so by similar triangles, I would have epsilon s prime over CNA minus d prime equals 0.003 over CNA. Okay, and then here epsilon s prime would be 0.003 here, let me write it better. It's normally we write it like this. We write it as CNA minus d prime over CNA times 0.003. So this would be, what is it, 7.14 inches? Was that what we had? Yeah. So CNA 7.14 minus 2.5 inches divided by 7.14 times 0.003. What's my strain?
0.0019.
0.0019. That's really close to yielding, right? The yield strain of grade 60 steel, which would be Fy over Es, is 60 over 29,000, is 0.00207, right? But nonetheless, it hasn't yielded, right? So that means I have to use Hooke's law. So this is less than epsilon y, and therefore Fs prime is Es times epsilon s prime. And so I go back here now, I go back to the equilibrium equation. I know As2, that was 2.20 inches squared times 60 ksi is equal to As prime times, by Hooke's law, 29,000 ksi times the strain in the steel, which is 0.0019. And so now I just have to solve for As prime. So As prime and what'd you get? 2.2 times 60 divided by 29,000 divided by 0.0019.
2.40.
Yep, 2.40 inches squared. So that is the compression steel As prime required. Like that. And that's it. That's it. And once you have those, now you select the bars, you check the spacing, the detail, probably check Phi-Mn greater than or equal to Mu one more time just in case, especially if you make some significant deviations from the required areas of steel. But those 7.03 inches squared on the tension side, that's what we need, and then the compression side 2.40 inches squared. The end. Structure free!